All right, well, thank you very much. I'm Alex Sehlke. I'm the PI on the TL project within ANGSA. Derek Sears is my co-I. Don't bother reading the long title. In short, it's glowing moon rocks probably can tell us where the water is on the moon. And to start this off, our overview, or just give you an introduction into this, is that we're interested in the TL because it can tell us something about the thermal and radiation history on the moon. And it's really the process of buildup of electrons into higher energy levels due to ionizing radiation. And then on the other hand, the drainage of these electrons due to heat. And understanding that this can tell us something about the thermal history on the moon, and with it, the thermal history comes where volatiles would be stable, especially on long-term, long millions of years over that kind of time frame. So resource sequestration is important, and we think that we can connect TL to that. You could do this kind of work that we're doing, and we'll present it here, is that we're doing it on return samples, but also you could do those kind of measurements if you had an instrument sitting on the surface of the moon doing these measurements. So what we really need to do is to get a better understanding of the TL in lunar samples. The earlier slide I've shown the reference that we're quoting on how to do this was developed, basically the theory was developed in the 1950s. And by the time Apollo 17 was approaching, there were some studies done on TL on the previous Apollo missions. And what it crystallized down to is that it would be wise to put samples into the freezer, because the argument was you would lose the TL or a great deal of information if you would keep those samples at room temperature and curation. And NASA was convinced, so they put some of the samples into the freezer while they also kept something or some of them at room temperature. And that's basically our basis of what we've been doing here, is that there's two sets of the same sample at different temperatures that we can exploit to do a 50-year experiment into the TL kinetics in lunar samples. So what I want to just do here is just to give you an idea of how this works is just look at the right plot on the top right hand on this slide. Is this is the glow curve that we would measure in the lab. On the x-axis is basically the temperature that we heat the sample up to and measure the light that's coming off. That's the y-axis. And for a sample that would sit on a illuminated surface that has around the temperature 370 Kelvin, you would see nothing until about 500 Kelvin. That's when we would see the first kind of glow coming in when we do these kind of measurements. And then imagine if there's a boulder rolling down the hill and casting a shadow on a previous sunlit surface, then the radiation could actually build up at lower temperatures, and then the whole glow curve would kind of like raise up over thousands of millions of years. And the two really important parameters here is the electron trap. See it as a activation energy of when these electrons will be falling out of their trap, and the Arrhenius factor, which is kind of it's basically the probability of the electrons wanting to get out of that trap. So these are the two things that we really have to determine to understand what's happening on, or how TL is decaying away over the years in these lunar samples. It's a thermal process in the end, and one of the equations on the bottom shows that. But if the theory is right, we can rearrange all these equations into the equation that I'm showing on here, in the middle of the slide, that we plug in all our parameters, and we could spit out a temperature. So within our project, we have basically samples from 3 different locations close to the lander, where we have a drill core. In this talk, I'm only focusing on the surface regolith because only measurements in the 50s and the 70s were done on these kind of samples. So we're looking at the sunlit, partially shaded, and permanently shaded surfaces here. So we got all of our samples in March, and that we could actually do the full study that we wanted to do. Here's just a slide, that's what it looks like in our lab. We're using about 4 milligrams of a sample per run, put in a tiny copper pan shown up on the top right-hand side of the slide. It's about 6 millimeter wide. Put it on a heater strip, put the PMT or the photomultiplier tube on top and heat up the sample and measure that glow curve that's coming in that's seen on the bottom in real time. All right, here's really the slide. That's the key essence of this talk. So at LPSC, I've shown basically the data on the top right is that we compared, by the time we only had the room temperature samples, that we compared the measurement done in, there's this thing in front of it. I can't move it. But the top curve basically is from 1976, the measurement, and then just now, almost 46 years later, it's the dash curve, that's our measurement, that shows that if you keep a sample at room temperature for a sample that should have been at a much colder temperature on the surface of the moon, the signal has faded away, about 40% roughly. And now the new data is shown on the bottom right is that if we keep that sample frozen, in that case it was -20 Celsius, that's roughly the temperature at which it was stored on the surface of the moon. Compared to the measurement then, we see that there's no decay. That really proves the point that the TL follows the rules that were laid out in the 50s in these samples from the moon. So it's a really important measurement. Just to put it in different words is that we could do fundamental science here by looking at these samples from the moon to understand the physical process that's happening in those kind of samples. So it was a really unique opportunity to do these kind of experiments and investigation. So to also put that into context, just to back out a little bit more. So what it is that our experiments tells us that, or that Apollo tells us using these samples, that going forward to Artemis would be probably wise to curate those samples at temperatures at least what the environmental temperature was, or even colder, just to preserve the TL signal. But it's not just the TL signal. We have heard it earlier in this session from Kate and Brittany that it follows the volatiles too, that this made an impact. So here it is. All right, just going more into a little bit detail into this. So we double checked what we did here just to plug in all the values. And what it tells us that the parameters that can pull out follow the theory that we have done. And just to give you an idea what it is, that the peak around 500 degree Kelvin is stable around between 40 and 60 years. And that's the time frame the samples were curated or the measurements were done in between back then and now. The higher temperature peaks are stable for up to billions of years older than the moon. So that's what we can pull out of these glow curves. All right, so going forward here, then is that what else we have to do to kind of pull out the temperature to give a really good estimate on what the storage temperature was of the sample is that we have to do more. We haven't gotten there yet because we hadn't had enough time since we received the samples, but we have to do an irradiation series that will figure out how many traps are there actually and how far can the TL signal build up that we can do our calculations to figure out what the temperature was, and potentially also how long that sample was stored at that temperature. And what we think now that we know that TL theory holds true, we can rearrange all the equation, and showing on the bottom plot in here is that that's what we think a glow curve could look like for a sample returned from a cold trap on the moon. But we have more to do. That's just kind of the theory, but using all the things that we found, this is what it could look like. All right, I think I've just said that. Let me double check. Yep, basically said that. But the one thing I haven't said was, is that we expect the values to be somewhere around 0.5 eV, so much lower energy traps. And at those temperatures, they will be stable for up to millions of years. So That's probably our upper estimate on what the history could be on these samples. Yeah, all right. And then the last thing is that we're also trying to build an instrument to send to the moon. In our lab, it's spread out over a whole bench. It's a big, old, setup of multiple components that we try to stick into a small box. And we got our first glow curves spit out from this little instrument, and it seems to work just fine the way we wanted it. So going to end here. So the next steps are doing more measurements on these samples, especially the irradiation, to really get a better understanding of what the TL saturation will be, to figure out the temperatures on the surface of the moon, particularly of the TLV. So we have the whole set of build core samples that we can apply this theory to maybe pull out a temperature gradient using the TL technique. That would come probably in LPSC. We have more to say about that. But what I really want to say is that the cold storage of the shaded samples really made an impact on the TL levels that we see, and that the TL decay is really following the theory. And that we think we can apply this to finding cold traps on the moon that were there for a long time, millions of years. So thank you.